Okay, we are here. Uh, yes. So when n2 become positive, then this part, the initial part will be sorry, the leading part will be red shifted and the trailing part will be blue shifted. While when there will be negative value of n2, then the case will be case will be opposite. When the n2 is negative, then the leading part will be blue shifted and the trailing part will be red shifted. So we'll be combining now these two quantities, the dispersion as well as the nonlinearity. Then we'll see what will be happening here. Now you see, for temporal Soliton formation, when there will be normal dispersion, beta 2 is greater than 0, then this will be the leading part will be the red shifted and the tailing part will be blue shifted. And when there will be a nonlinear effect when n2 is negative, then the case will be like this: the leading part will be blue shifted and the trailing part will be red shifted, totally opposite to each other. Okay, so when normal dispersion occurs, when beta 2 is the positive and dispersion is negative, then this case will be occurring. So then what will happen when these two pulses merge together? One, because of dispersion only, this effect is appearing into the pulse, and because of nonlinearity alone, this effect will be appearing into the pulse. When both these two are present here, when the normal dispersion as well as negative refractive nonlinear refractive index is there, then what will happen? They cancel each other's effect and there will be a formation of soliton. This is the pulse which were launched into the fiber. uh, this is the pulse shape of the pulse which was launched at the fiber. So in the output also we are getting the same pulse, same with same amplitude, same frequency. So this way the soliton will be occurring. Now if there will be anomalous dispersion and there must be a positive refractive nonlinear refractive index, because of which they will be cancelling each other's effect and there will be a safe preserved uh, soliton soliton propagated towards till the end of this fiber. Okay, so these are the two cases when temporal soliton is formed. Now coming to the spatial soliton. Spatial soliton is related to the width of this beam of this uh, the pulse. Here, if the pulse is of this form, say for example this is x. Okay, in the x direction, the shape of the pulse, the intensity pattern of the pulse is like this. And say for example there is a car medium, and because of this car medium, what will happen? Say for example the non this this is the fiber and the fiber is having dispersion. Then what will happen when light will be this pulse will be propagating through this medium? Then there will be a production of, due to the dispersion of this medium, the pulse will be dispersed like this. Okay, so uh, this medium will be behaving like a concave lens. So since the pulse get dispersed at some certain point, so if we see the focal length, then that will be LF, L focal length, which will be in the negative direction. So this is the defocusing due to diffraction. Then okay, there may be, if this is a car medium, then the self-focusing due to nonlinear effect n2 is greater than 0 may be appearing. If self-focusing will be there, then the pulse will be focused at some certain point, up to some certain point, end of this medium. So let us check, let us call this f is the same distance. F is now plus LF. Okay, now this medium will be behaving like a lens, convex lens, which is focusing the light. So due to diffraction, light get dispersed, and due to self focusing, light get focused. So focusing, defocusing and focusing are appearing because of these two terms. One is diffraction, one is self focusing. Okay, if both these two effect appear together, diffraction and nonlinear effect, then there will be a production of soliton. How? They here f is negative, here f is positive. When f will be lf minus uh, lf, that will be 0. So focal length will be 0. If focal length is 0, then the pulse will be propagating without any attenuation or without any self focusing throughout this fiber, and that will be giving us the spatial soliton. So this is the case of spatial soliton. Now we have in the temporal part, we have bright and dark solitons. We have the nonlinear Schrodinger equation. Here we have this is the shape. This gives the shape of this pulse. This is the dispersion, and this is nonlinearity. Now, exact soliton can be obtained when pulse has initial shape, which is a function of is kind of sec hyperbolic pulse, and then when n is greater than or equal to 0, then if uh, when this sec hyperbolic pulse appears, then as a solution of this nonlinear Schrodinger equation, then we can get a very beautiful positive uh, or bright soliton. And the soliton can be negative also. Analytical soliton for to nonlinear Schrodinger equation for dark soliton is, this is tan hyperbolic. If tan hyperbolic pulse is there, appears as a solution of this nonlinear Schrodinger equation, then we can get a dark soliton. In the dark soliton, there will be a peak dark line, and in the uh, bright soliton, there will be a bright line here. Okay, so these are the two kind of temporal solitons, which are dark and bright. And for bright soliton, we have the soliton solution is sec hyperbolic, and for dark soliton, it is 10 hyperbolic pulse. Okay, up to this we uh, finish our discussion. So this is the end of this course, MSP 403D, laser and nonlinear optics, and hope you have learned a lot from these discussions. And if you have any queries, please communicate with me. My WhatsApp is available, and you can also call me directly. And I'll be giving one assignment in the next class, that will be final close down of this course. And till this we are finishing the course of laser and nonlinear optics, the 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 nonlinear optics parts. Okay, thank you. I wish you to be home at home, and be safe. The situation is getting worse and worse, so uh, be safe at home, and thank you so much.